Hello everyone, today we talk about the practical matters of developing and testing the Pig script. Pig provides several tools and diagnostic operators to help us for developing the Pig applications. First, the syntax highlighting and checking. The syntax highlighting often helps us to write code correctly. And even though Pig can be edited in text editor, these following tools can help us for syntax highlighting and checking, including Eclipse, Emacs, TextMate, and even vim. Describe shows the schema of a relation in the script. This can be very helpful when we are developing our script. This is especially useful when we are learning Pig-Latin and understanding how various operators change the data. Describe can be applied to any relation in the script, and you can have multiple describes in your script. Here is an example, describe.pig. So the data is read from the NYSE dividends data set, and it's trimmed by the for each operator, and then grouped by, and then for each group generate the group and average. Then after those operators, we can describe these three relations we generated and see how these operators work on the data and generate new relations. Describe uses Pig's standard schema syntax. Explain. One of Pig's goals is to allow users to think in terms of data flow instead of MapReduce. But sometimes we need to see how Pig is compiling our script into MapReduce jobs. Pig provides explain for this, for the execution plans. Explain is particularly helpful when we are trying to optimize the script and debug errors. It's written so that Pig developers can examine how Pig handled various scripts, and its output can help us to write better Pig-Latin. There are two ways to use explain. We can explain any alias in the Pig-Latin script, and it will show the execution plan Pig would use if you store that relation. Also, we can take an existing Pig-Latin script and apply explain to the whole script in ground. So it has a couple of advantages. First one, we do not have to edit the script to add the explain line. The second, it will work with scripts that do not have a single store. It will show how Pig will execute the entire script. Here is an example of the same. This is the same. This is very similar to the script earlier. So it grouped the dividends data, and for each group it generates group and average dividend. Then store this average dividend into a file. Then in the command line, when we run this script with explain, we add this -e explain this script. Pig goes through several steps to transform a Pig-Latin script to a set of MapReduce jobs. After doing basic parsing and semantic checking, it produces a logical plan. This is an example of the logical plan for the previous pig-Latin script. This plan describes the logical operators that pig will use to execute the script. Some optimizations are done on this plan. For example, filters are pushed as far up as possible in the logical plan. So in this example, we can see that the flow of this chart is bottom to up to top, so that the load operator is at the very bottom. The lines between operators show the flow. Each of the 4 operators created by the script, the load, code group for each, and store can be seen. Each of these operators also has a schema described in standard schema syntax. The code group and for each operator also have expressions attached to them. In the code group operator, the projection indicates which field is a grouping key. In this case, field 1. The for each operator has a projection expression that projects field 0 and a UDF expression, which indicates that the UDF being used is org.apache.pig.builtin.avg. Notice how each of the project operators has an input field indicating from which operator they are drawing their input. Adding the dash dot operation, the logical plan will be printed in a logical plan diagram. This is a corresponding logical plan for the previous example. After optimizing the logical plan, pig produces a physical plan. This plan describes the physical operators pig will use to execute the script. The physical plan for our example is shown in this figure. It looks like the logical plan, but with a few differences. The load and store functions that will be used have been resolved, and the actual paths that will be used have been resolved. This example was run in local mode, so the paths are all local files. The other difference is that the code group operator was replaced by 3 operators: local rearrange, global rearrange, and package. Local rearrange is the operator pig uses to prepare data for the shuffle by setting up the key. Global rearrange is a stand-in for the shuffle. Package sits in the reduce phrase and directs records to the proper bag. This is a graphical representation of the physical plan. Finally, pig takes the physical plan and decides how it will place its operators into one or more MapReduce jobs. First, it walks the physical plan, looking for all operators that require a new reduce. This occurs anywhere there is a local rearrange, global rearrange, and package. After it has done this, it sees where there are places that it can do physical optimizations. For example, it looks for places the combiner can be used, and whether sorts can be avoided by including them as part of the sorting Hadoop does in the shuffle. After all of this is done, pig has a MapReduce plan. MapReduce plan describes the maps, combines, and reduces. Along with the physical operators pig will perform in each stage. In our example, this is the MapReduce plan shown on this page. It looks similar to the physical plan. The pipeline is now broken into 3 stages: map, combine, and reduce. The global rearrange operator is gone because it was a stand-in for the shuffle. The AVG UDF has been broken up into 3 stages: initial in the map, intermediate in the combiner, and final in the reduce. If there were multiple MapReduce jobs in this example, that would all be shown in this output. This is a graphical version of the MapReduce plan. When we want to debug our pig-Latin script, we run our data through the script. But when we are working with pig on a large data set, it will take a long time to process the data and makes it a very long debugging cycle. One solution is to run the script on a sample of the data, but this only works for simple script because the sampling has another problem. It's not always trivial to pick a sample that will exercise the script properly. For example, if we have a drawing, we have to be careful to sample some records from each input, such that at least some of them have the same key. Otherwise, the drawing will return no results. To address this issue, Yahoo Research built Illustrate into Pig. Illustrate takes a sample of the data and runs it through the script. But when it encounters operators that remove the data, such as filter, join, etc., it will make sure some record can pass that operator and some do not. When necessary, it will manufacture records that look like the data, but they will have the same schema, even though they are not in the sample. For example, if our script has filter dividends by D is greater than 2009 January the 1st, then every record that Illustrate sampled had a value of less than this date. Illustrate will keep at least one of these records, and it will manufacture a record with D greater than this date. To use Illustrate, we can apply it to an alias in our script, just as we can describe. And this is an example script for Illustrate. This is a Illustrate output. In this example, in the filter dividends by D greater than 2009 January the 1st, this filter would remove no records in the input to show how then we can see how Illustrate can manufacture records that will be removed. And like explained, Illustrate can be given as a command line operation rather than modifying the script. Beyond the tools covered previously, there are a few things that are useful in debugging pig-Latin script. First, if Illustrate does not do what we need, we can use local mode to test the script before running it on the cluster. And a second tip is sometimes we need to turn off particular features to see whether they are the source of the problem. This can include particular optimizations that pig attempts or new features. This table lists features that can be turned off. All these are operations that can be passed to pig on the command line. As part of the development, we will want to test the pig-Latin script. Pig unit provides a unit testing framework that plugs into JUnit to help us write unit tests that can be run on a regular basis. Here is an example of how to test a script with pig unit. First, we will need a pig script to test. And second, we will need the pig unit.jar file. This is not distributed as part of the standard pig distribution, but we can build it from the source code included in our distribution. Third, we will need data to run through the script. And the last, we will need to write a Java class that JUnit can use to run the test. This is a simple example that runs the previous pig script. We can see that an instance of pig test is created that it uses the pig script, and then the expected output is specified. Then the test will run the script and check if the output matches the given expectation.